So let me begin with what I mean by cyclic characters. Suppose if we have a group G and then consider any element small g in this group. Suppose the order of this element is m. What we can do is we can always consider the cyclic group subgroup generated by this particular element. This will be a cyclic group of order n. I'm denoting it as Cm. Now, the irreducible characters of this group are given by the primitive mth roots of unity. So, theta to the theta m I denote to be a primitive mth root of unity. So, how the irreducible characters here, the irreducible representations are just one dimensional. So, the irreducible characters or irreducible representations are same. Like it's just one dimensional representation. So, how the irreducible characters are defined is for every I, that is I ranging from 0 less than or equal to I less than n minus 1, we have this irreducible character sigma I, which maps the generated G to the ith power of this mth root of unity. So this is how the irreducible characters are given. Now, what we want is cyclic character. By cyclic character, what I mean is this induced character from the cyclic subgroup to the group. So, what we have here is we have a group G. Now, we have a cyclic subgroup Cm that is actually generated by a particular element in this group G. Now, we have a irreducible character here and denoting it as theta m to the power I. Now, when we induce this, this will be a character here, something I denote it as psi. So, suppose if we have a character in this cyclic, just for the sake, I'm considering the irreducible character. The irreducible character in this cyclic subgroup, I'm inducing it to the group to get a character here. This induced character is called as the cyclic character of this particular group. Now, the problem I am interested in is, so what we have is when we induce this, we will be getting, so what we are doing is we are inducing an irreducible character from the cyclic subgroup to the group. When we induce this, we will get a character in the bigger group. And this, suppose if rho I is the irreducible representations of this group G, the psi can be written as, we know that every representation can be written as a direct sum of some irreducible representation. So this will be some Ci rho I. So the Ci denote the multiplicity, each how much time each irreducible representation occurs. So the problem I am interested is instead take my group to be equal to the case of alternating group. Now I need to understand when I take any irreducible character in the cyclic group generated by any particular element in this alternating group and induce it to get a representation in an alternating group, with what multiplicity each irreducible character occurs here? That is what my question is. So basically, I'm interested in finding out this Cm for each irreducible character here, or basically I can say for each character in this group in the cyclic subgroup generated by any particular element, I want to understand the decomposition into irreducible representations or irreducible characters. I hope the question is clear. Now let me begin with a literature survey that like what is already there. So this was first considered by Kraskiewicz and Weyman in 1987. They did it for the case of Coxeter group, but they didn't consider all the elements. They just considered only the Coxeter elements. Further, this was extended by Stembridge for all the cyclic characters in the case of symmetric groups and rate product groups, and few particular cases for the complex reflection group. And this after Garcia has also given a different proof in one of her book for the case of the symmetric group, and there is another proof for the case of symmetric group by Jöllenbeck and Manfred Schocker using the Lee, something called as Lee diagram. So this is basically a history of what is already there in the literature. As I have told, so the cyclic character for the case of symmetric group is well known. Now, so I will just give you a review, an overview of what is happening in the case of symmetric. So for that, let me just, maybe you all might be very familiar with the representation theory of symmetric group. Just for the sake, I will recall it. So how the representation theory, how the representations are understood here is like, For every, so suppose if I am considering the symmetric group on n letters, for every partition of n, we will be having an irreducible character or an irreducible representation of symmetric group. By partition, I mean an non-decreasing sequence like lambda 1, a tuple of elements, lambda 1, lambda r, that such that lambda 1 is greater than or equal to lambda 2, greater than or equal to lambda r, and the summation of lambda I running from 1 to r is equal to n. This is what I mean by a partition. So corresponding to each partition, we will be getting an irreducible character in the symmetric. Now, corresponding to each partition, we can also have something called as the N diagram. By an N diagram, what I mean is just a northwest aligned boxes. So if I have, if I denote my partition to be equal to lambda 1 up to lambda r, what I will be having is, the corresponding N diagram will be a boxes, a set of array of boxes that is aligned to the northwest corner in such a fashion that we will be having lambda 1 boxes in the first row, then lambda 2 boxes in the second row, and so on. For this particular example, 3, 2 is a partition. Here, the 3, 2 is a partition of 5. So, we will be having 3 boxes in the first row and 2 boxes in the second row. So, corresponding to every partition, we are having an irreducible character. And corresponding to every partition, we can also consider its N diagram. Now, we can also, there is also something called as a conjugate of a partition. What I mean is just flip it along the diagonal. We will get the conjugate of the partition. Just flip the this particular N diagram along the diagonal. We will get something called as the conjugate of the partition. So here it was 3, 2. When we flip it, it will be turning out to be equal to 2, 2, 1. So this is the conjugate of this partition. Or either way, you can also think that it is just simply interchanging the rows and columns, whichever way you want, you can consider it like that. Please note here that some partitions, for example, if I take partition to be like 2, 2 or 4, a partition of 4, here what will happen if we flip it, nothing will change. It will be the lambda, if this is lambda, when we flip it, nothing changes. So lambda prime. So it can happen that when you flip, it is not necessary that when we conjugate, we will get a new partition. Sometimes it happens that when we conjugate, we will get the same partition. Such partitions we call as self-conjugate partition, just for your information. So basically, this is something about the tableaux and stuff. Now, I need to introduce something called as the standard N tableau. What I mean by standard N tableau is, now, what we have seen is corresponding to every partition, we will be having an N diagram. In the N diagram, we have 5 N boxes basically. So, in that previous example, we were considering this partition 3, 2 or 5. So, there will be 5 boxes, 3 boxes in the first row, 2 boxes in the second row. In total, we will be having N boxes in the N diagram of the partition of N. What we can do here is fill the boxes with the integers 1 to n in such a fashion that when you go from left to right or top to bottom, in both cases, the numbers should be in an increasing order. This is the only condition. Okay, you can consider, so in case if you want, we can also consider like the only condition is it should increase along the row and column. So this is also an example of a standard. Sorry, I made a mistake. So maybe 1, 2, 3. So this is also an example of a standard N tableau. So basically, the only thing is when we go along the row and column, the numbers should be in an increasing order. We have to fill the N boxes with integers 1 to n, such that when we go from left to right and top to bottom, it should have an increasing order. Now, I need to define, so basically what I'm trying to explain is how the cyclic character, multiplicity of irreducible characters in the cyclic character of symmetric group appears. So for that, I am trying to define some more things called as the descent set of tableau, standard N tableau. What I mean by descent set is that we will say that there is a descent in I if I plus 1 appears in a row below I in P. So in the descent set, I will be in the descent set if and only if I plus 1 is in a row below I in the standard N tableau. For example, in this particular running example that we are considering, we have 1 and 2 below it. Similarly, we have 4 here and 5 in a row below it. So here the descent set is 1 and 4. Okay, the descent set is just 1 and 4. Using this, I also want you to introduce to something called a statistic on this standard and tableau called as the major index. By major index, what I mean is simply the summation of all the elements in the descent set. So in this particular running example, the descents are in 1 and 4. So the descent set, the summation will give you the major index of this particular standard and tableau. That is 1 plus 4 is equal to 5. So for every tableau, we will have something called a standard and tableau. And for every standard and tableau, we are defining something called a statistic called as the major index, which is the sum of descents. Now, so what I was telling is like what we are, let me just recall the problem once more for the sake of clarity. We started with a cyclic group generated by any particular element G in G. Now we are considering the group, the induced representation from this irreducible represent. If I pick any irreducible character here, I'm just inducing it into this group. I want to see with what multiplicity each irreducible character of G occurs in that induced representation. So if I, for the case of symmetric group, I'm picking, what I'm picking is I'm picking the element itself to be the n cycle. Okay, this is our G in capital. Our capital G is the symmetric group and this is the small g. This is the element I am choosing. So let me recall you again that this problem is well known for all the elements in the symmetric group. But for the sake of in this talk, in the case of alternating group or here, I will be only explaining with the case of the n cycle because let's understand it what is happening. To generalize it, it's just follow the same procedure. So I'll be only considering this particular case where we are picking only the n cycle. Here, the multiplicity. So yeah, this needs a little bit understanding. So this is something called as the inner product of the characters. So what I'm doing is I'm picking the irreducible character in the cyclic group generated by this particular element, that is theta n to the power I. I am inducing it to Cn from the cyclic group to the symmetric group. Now the question is with what multiplicity for in symmetric group the irreducible representation characters are given by chi lambdas. So with what multiplicity each chi lambda occurs. So when we take this inner product, we are actually getting the multiplicity, with what multiplicity this particular chi lambda occurs in this particular induced representation. And we will be denoting this as A lambda I. So basically what it means is like this induced representation Cn to Sn of theta n to the power I is the direct sum of some A lambda I rho lambda, where lambda is a part, sorry, not rho lambda. I was using the notation by lambda. Direct sum of the partitions of n, a lambda I chi lambda. Okay, this is what I. So this a lambda I is with what multiplicity chi lambda occurs in this particular induced representation, theta n to the power I. And for the case of symmetric group, this is given by this number. That is the number of standard n tableau of shape lambda whose major index is congruent to I modulo n. Let me explain this with our example. So this is the standard, this is the all possible standard n tableau of shape 3, 2. Okay. Now, what I want to do is like we need to find the major index of each of the standard n tableau. So where is the descent occurring? Here we have a descent in 3, here we have a descent in 2 and 4 because 3 and 5 appears below. Here we have a descent only in 2, here we have a descent in 1 and 4, and here we have a descent in 1 and 3. Now what is the major index? We just have to sum this over all the major or the descents. So here it is simply 3, here it is 2 plus 4, that is 6, which is congruent to 1 modulo 5. Here it is 2, here it is 1 plus 4, that is 5, congruent to 0 modulo 5. Then it is 1 plus 3, that is 4. Now, what it says is like the number of times each number appears, like, so A lambda I is the number of times I appears here. The number of times 3 appear is 1 time. So here basically in this example, in this particular example, I have chosen each number ranging from 0 to 4 appears 1 time. What it says is like if I induce any irreducible representation, of the cyclic group generated by this n cycle to the symmetric group, each of the each of this induced representation will have a single copy of this particular irreducible character, or if this particular character indexed by this particular partition. I will repeat it once more. If I induce any irreducible character of the cyclic group generated by this n cycle, we will have a single copy, a unique copy of the irreducible character of symmetric group indexed with this particular partition. This is what it says. Or in other words, what I can say is, so there is something called as Frobenius reciprocity. If you have seen a first course in the representation theory, you might have seen this. That is, this is same as if I take theta n to the power I, and if I restrict this Sn to Cn, this particular chi lambda. That is, if I restrict chi lambda to Sn, from Sn to Cn, this will be a direct sum of irreducible representations in this cyclic group. Okay, so what this in this particular example, what it says is like, if I take this particular partition 3, 2, what is happening when I restrict it? It is simply the direct sum of all the irreducible representations of the cyclic group generated by the Cn, where each irreducible character appears at exactly one time. Okay, I hope this is clear. Now I am moving on to the case of alternating group. So for the case of alternating group, let me first help you to understand how the irreducible characters are given. So in the case of alternating group, the irreducible characters we study from the irreducible characters of the symmetric group. So we will be considering here two cases where lambda is not equal to lambda prime. That is, where lambda and its conjugate are different. In this case, so we have lambda and we have its conjugate lambda prime. When I restrict chi lambda or chi lambda prime from Sn to An, both will be restricting down to a single irreducible representation, or the same irreducible representation in An. There is a notation upset, but the notation is not good, but what I want to tell here is like, if I restrict chi lambda or chi lambda prime, both will be restricting down to a same irreducible representation in the alternating. So what this says is that their characters are same. So if their characters are same, what is happening? If I take the inner product in San, or if I take the inner product in symmetric group, it doesn't changes. So basically, this value remains changes. If lambda is not self-conjugate, the multiplicity of that particular character in alternating group or in the symmetric group are same. Now, what happens if lambda is self-conjugate? That is, lambda equal to lambda prime. Then, what is happening is, when we restrict chi lambda to San, it splits into the direct sum of two irreducible representations or two irreducible characters in the alternating group that I denote it as chi lambda plus and chi lambda minus. So here we will be having two different multiplicities, which I denote it as a lambda I plus and a lambda I minus, for chi lambda plus and chi lambda minus. Now, I want to explain what I need is, I was trying to give you what is the character value. So we have only a glitch here in lambda is self-conjugate. So in this case, I'm introducing a small definition kind of thing. It's just simple. So what I want is, I'm defining something called as folding of a partition with distinct odd parts. Only I'm defining something as a folding only for a partition with distinct odd parts. So what is happening is, consider this particular example. Here we have 9 boxes in the first row, 5 boxes in the second row, and 3 boxes. So this is a partition of 9, 5, 3. This is this particular partition. And so here we have distinct odd parts. Suppose if we have such a partition or an N diagram corresponding to this, what we can do is, we can fold this to get a self-conjugate partition. How we will do this is, just fold it in the first row, in the middle. Then you will get something as a whole. Now repeat the same procedure for the next 2 rows. Then we will get something like this. So whenever we fold a partition with distinct odd parts, we can get a self-conjugate partition from that. Here, when we flip it, nothing is going to happen. It's basically the same because we are just folding it in the middle. maybe this is how we just explain the one-to-one correspondence between partition with distinct root parts and the partition with and a self-conjugate partition. Let me recall again here. As I told, for this particular talk, I am only concentrating when the group element. So we were considering a group element G, and we were inducing the character to G. So in this particular case, in this talk, we are only dealing with the case when G is the end cycle. Okay, and note that we are dealing with the group alternating group. In alternating group, the end cycle. If I pick any end cycle 1 to n. This will be an element in the alternating group only if n is an odd number. So here, if I consider this particular n cycle, the folding will be looking of this form. Okay, there will be n plus 1 by 2 boxes in the first row and a single boxes till n minus 1 by 2 rows. Okay, just I want you to keep this in mind. The folding of an n cycle will be of this particular partition, n plus 1 by 2, comma 1, 1. How the character is given is now the question. So if lambda is a self-conjugate partition, then we will be having two irreducible characters, chi lambda plus and chi lambda minus. Now what is happening is, if so what we are doing is we will be evaluating chi lambda plus chi lambda minus in some particular element in the alternating group. This is how we evaluate the character. So what I want to consider here is again two different cases. That is, suppose by W sigma, I mean an element of cycle type sigma. And this cycle type means sigma will be a partition of it. So if this partition is a partition with distinct odd parts such that when we fold it, we will be getting lambda. Remember that lambda is a self-conjugate partition. So suppose sigma is a partition such that when we fold that particular partition, we will be getting an element, we will be getting our lambda. Then the character value is given by this particular formula. Note that my notations are given here. Note sigma is a partition with distinct odd parts such that when we fold it, we will be coming back to lambda prime. If there's note that there will be a unique such partition. For every lambda, we'll be getting only a particular sigma like that. In this particular case, it also happens that chi lambda plus minus value in W sigma minus. Just like so there is a one-to-one correspondence between the conjugacy class and the irreducible characters or the irreducible representation. So the irreducible characters will also be, so the conjugacy class also splits here. So that's why we have W sigma plus and W sigma minus. Now, if it is not the case, if sigma is a partition that is different from the particular partition, that is sigma is a partition whose folding is not equal to chi lambda, not equal to lambda, then the value, the character value evaluated is simply half of the character value in the symmetric group. Okay. So in this particular case, we were looking, just recall that we are looking only the case when W is an n cycle. And this n cycle, when we fold it, we will be getting this particular partition, n plus 1 by 2, comma 1, 1, 1. So what I want to say is, if our lambda is a partition different from this, the character value was simply half of the character value of the symmetric group. So here I made a mistake. Yeah, this is that. So what I want to say is, like, since the character value is nothing but the same as half of the character value of the symmetric group. So what will happen is, all the remaining cases where lambda is any self-conjugate partition that is not equal to this, in all such cases, the multiplicity is simply half of the multiplicity in the case of the symmetric. Now, what will happen is, so we only need to consider the only particular case that is remaining is lambda is a self-conjugate partition that is exactly equal to this hoop partition, n plus 1 by 2, comma 1, 1, 1. To deal with this, just recall that a lambda I, we can denote it as a lambda, we can write it as take it into the sum of multiplicities in the case of alternating group. Because what we are doing, we are starting with the cyclic group here, we have alternating group here, we have a symmetric group here. So when we induce it, we will be having chi lambda plus and chi lambda minus, and here we will be having our chi lambda, self-conjugate partition. When we induce it to the symmetric group, this is how it is happening. So basically the multiplicity here, so if what will be happening, since the induction is associative, I can tell that a lambda I plus a lambda I can be is simply the sum of these two multiplicities, a lambda I plus and a lambda I minus. Let's just denote their difference to be the capital delta lambda. Now it's clear, if you know one of like if you are able to find this particular value, we are done. This basically gives us what is a lambda I plus and a lambda I minus. So now our target will be simply to find this difference. Let me explicitly write this difference. So the difference means I am actually want to find the multiplicity. Just recall here again, I am rewriting, we were actually considering the problem with induced representation, but by using Frobenius reciprocity that I have explained earlier, we can just rewrite this in terms of the restriction. So again, just applying the formula for the inner product of characters, I will be breaking down this into these two sums. What I have done is, like, we know that there will be two conjugacy classes here. So here I have split this into the summation into terms of two conjugacy classes. Okay, and we have also seen that in this particular partition, when the folding is actually equal to this particular partition, this condition is followed. So I can take this character difference outside, and the summation will be changing into a negative sum here. This is how it happens. Now what we have, we need to understand capital delta lambda I. We know this from the theorem. What is remaining is we just need to understand this particular sum, where it is the sum of some particular primitive nth roots of unity, some particular powers of sum of primitive nth roots of unity. For that, we have also one more thing. We need to understand when will be this, how for what k it will lie in the conscious, or how the conjugacy class is given. For that, let me. So what we need to understand, we need to this W sigma is our n cycle. So the n cycle will be conjugate to W sigma to the power k. In the case of symmetric group, we know that the elements are conjugate if they have the same cycle type. So here it will remain as an n cycle if and only if the GCD is equal to 1. And for the alternating group, what the condition we need, there existed element in the alternating group such that when we conjugate it, we will be getting W sigma to the power k. So here I am again only considering the case when n equal to p to the power a. Extending in general is easy, but just consider the case when n is a power of an odd prime. So k will be the generator of this multiplicative. Suppose k is the generator of this multiplicative group. Consider this element. Now this will be conjugate for all k with GCD if and only if this a is even. And whenever a is odd, we will be having an odd permutation. Just keep this in mind. And I want to introduce one more number theory notation, that is the Jacobi symbol, or I think Legendre symbol. So k by p to the power a is simply k by p to the power whole of a. How it is given is, it takes three values, 0, 1, minus 1, depending on whether it is a multiple of this prime p, or if it is not a multiple but it is a square modulo p, or otherwise it will be having minus 1. So using this notation, I can rewrite this statement, the previous statement that we have received as, if n is any, so again here I just mentioned only for the case of p to the power a, I will be able to get this theorem or this lemma in general by using the Chinese remainder theorem. I am not going into the detail of the proofs. So if n is the product of this prime, then odd primes, then w and w to the power k are conjugate if and only if this Legendre symbol is equal to 1. This is my condition. So what I can do is, like, let's recall we were in the like our target was to find this difference, capital delta lambda I. So here we were looking on to this difference. Now we have seen that this both are conjugate if and only if the Legendre symbol is 1, and if it is not conjugate, the Legendre symbol is minus 1. So I can replace this minus with this particular thing. Okay. Now this is just the formula to find so what we need is, we just need to understand the summation, and we can get the summation using from this lemma. yeah, this is basically nothing. The idea only we used here is simply the Gauss directionalism, and just with a computation we will be able to get this. Here note that my notation for epsilon p is simply 1 if p is 1 modulo 4 and minus 1 if p is congruent to 3 modulo 4. Just recall that this I am looking only to the case of n cycle, and the n cycle will be in the alternating group only if n is an odd number. That's why here everything I am looking only for the case of odd number. Now, this is my final theorem, which gives me the value of capital delta lambda I. So, as I have mentioned, delta lambda I was the difference of a lambda I plus and a lambda I minus. And once I get this value, and I also know that a lambda I was a lambda I plus a lambda I minus. So I just added only this value of delta lambda I. From this, we can actually get the value of a lambda I plus and e lambda I minus, which was our. So yeah, I mentioned here in this talk, I was only considering the case of cyclic characters from the n cycle. But for the general thing, we just need to like the Gauss sum and everything, just check on each prime factors. Okay, that's how it works. And this is here is my references. This is one of our ongoing.
Thank you, Amrita, for the nice talk. We can have a quick question if any one of you have. Okay. Maybe we can have questions during the tea break or coffee break. Yeah. Thanks a lot.
Thank you.